Hi everyone, I'm Joon Sern, the principal investigator for this research problem in Ensign InfoSecurity, Singapore. Ensign is the largest pure-play cybersecurity service provider in Asia. As part of our ongoing efforts to differentiate ourselves from the competition, we conduct deep technical research into some of the hardest problems in cybersecurity. In this presentation, we will talk about how we created an interpretable, deep learning-based method to classify malware types into their respective families, achieving better performance than the current state-of-the-art in this field. In particular, we propose an approach based on both supervised and unsupervised learning. This enhances the performance of malware family classifiers. The agenda for this presentation is shown here. First, we will introduce the problem. Next, we will highlight some of the important literature and their achievements in this field. We will then state the objective of our research and describe our methodology. Following that, we will showcase our results and then conclude the presentation with possible future work and enhancements. Now, let's introduce the problem. The rapid digitalization in recent years, driven in part by the pandemic, has resulted in a significant increase in cyber attacks. In 2021, governments worldwide experienced a 1,885% increase in just ransomware attacks. In fact, cybercrime has become such a lucrative business that malware as a service is booming. As a result, the number of malware samples has increased at least 106% year-on-year in 2021. This sudden surge in malware activity poses a huge threat to cyber defenders because the large increase in malware variations may render conventional signature-based techniques less effective. In fact, small variations in the malware by malware service providers would almost certainly be able to evade conventional hash comparison and ASCII string analytic techniques. The reason is the strict pattern matching involved in such methods would typically fail to pick up malware binaries with even minor variations. Byte pattern matching may be more robust depending on the specific technique used. Notwithstanding this, recent studies showed that around 3/4 of malware samples collected in 2021 can already evade traditional signature-based security tools. Thus, the detection and classification of malware is a real problem, and there is an urgent need to improve capabilities in this area quickly. Recently, there has been a sudden surge in malware activity, but it has actually already been on the rise since 2010. The researchers have been actively trying to address this problem. Here, we will review some of the relevant past work. Before delving into the details, it should be noted that a lot of research attempts to detect and classify malware into their families because this would give malware analysts more context as to the malware's functionality, aiding incident responders in zeroing in on what impact the malware might have had. In 2011, Nataraj published a seminal paper that showed the possibility of applying image analytics to the malware classification problem. In particular, he was the first to show that converting the malware binary to images, such as the 4 examples above, and then applying standard GIST descriptors, resulting in the ability to differentiate malware among the 8 families. Particularly, he showed that the embeddings of malware from these 8 families could be well clustered into 8 different clusters as shown in the diagram below. In fact, by looking at the 4 examples above, it is clear that there are textural similarities among the malware of the same family. For example, the GAN crab family has 2 dark lines near the top, and the malware from the Agent Tesla family has diagonal lines spanning from the top right to the bottom left. This is the hypothesized reason why image analytics could work to differentiate among the different malware families. In 2017, Makanda et al. Built on this work by adding additional features. On top of GIST, he applied the discrete wavelet transform to obtain another set of vectors. The 2 vectors were then concatenated and then passed to a deep neural network consisting of multi-layered perceptrons, or also known as dense layers. With these features, the multi-layered perceptrons are then trained to conduct the classification over 8 families, with the extracted feature vectors as input. In 2021, Prajapati went further by exploring the application of other more recent neural network architectures to this problem. In particular, instead of human-defined GIST descriptors and discrete wavelet transforms, CNN and RNN architectures were used to extract salient features from the raw image data. The entire neural network was then trained end-to-end with the raw image data as the input, to output a classification as to which malware family it probably belongs to. It should be noted that all the previous works that we have reviewed thus far involved training deep neural networks using the softmax cross-entropy loss as defined in the equation here. This is the typical loss function used to train multi-class classifiers because it is a convex loss function. Thus, classifier neural networks are normally trained end-to-end via this loss function in a fully supervised manner. However, in 2021, multiple researchers started presenting their findings about how incorporating self-supervised techniques with supervised learning can improve the final performance of models. In particular, he showed that pre-training an image-based classifier via a masked autoencoder, which randomly masked input pixels as shown in the top figure, allowed it to attain improved performance for image classification tasks. Separately, in the same year, Bao showed a similar concept, but with transformer-based neural networks. So to summarize, these two works involved pre-training a neural network to reconstruct its masked input in a self-supervised manner without labels, followed by training via the softmax cross-entropy loss, which is essentially the supervised learning step. The conclusion of these two works was similar in that training the neural networks using a combination of both self-supervised and supervised learning techniques results in better performance. In 2022, Bevsky from Meta released the Data2Vec framework, which was touted to be the first modality-agnostic framework to be tested over multiple domains, particularly image, speech, and language. It is largely similar in principle to the earlier two works as it involves masking the inputs. However, instead of employing autoencoders, which involves encoders summarizing the input data, and decoders reconstructing the input data via the encoder's output, the Data2Vec framework is actually based on a knowledge distillation approach. In this approach, there are two networks, the teacher network and the student network. Both of these networks are identical in architecture and they are designed to ingest either images, speech, or text and output a series of vectors. The student network is fed with masked inputs and the teacher network is fed with unmasked inputs. Throughout the training process, the teacher network's weights are parameterized with an exponential moving average of the student network's past weights. And the student network is trained to reduce the distance between its output series of vectors and those output by the teacher network. Bevsky showed that pre-training neural networks with this framework allowed them to achieve at least comparable results against other state-of-the-art algorithms for each of the three modalities. Having reviewed the literature, we would like to answer two questions. First, Data2Vec has been well tested on conventional images with clear, distinct object-based features. Does it work well on malware binary images that are quite different from the objects we see in the real world? Secondly, conventional deep neural network models operate like a black box. Can we improve the model interpretability? To address the two problems, we propose the BinImg2Vec framework. As can be seen, it comprises two neural networks, a convolutional neural network, and a multi-layered perceptron. The purpose of the CNN is to extract salient features from the images, while the MLP is supposed to act as a feature analyzer to analyze the features extracted by the CNN and provide a classification as to which family the malware probably belongs to, given the features. The other important consideration is how to train such a neural network. We propose a composite loss function comprising the standard softmax cross-entropy loss and the Data2Vec loss. In particular, the softmax cross-entropy loss will be used to train both the CNN and MLP in an end-to-end fashion using the labels we have from our dataset. This is identical to how conventional deep learning models are trained. The main difference is our second pipeline where we integrate the Data2Vec framework. To do this, we make a copy of the CNN labeled here as the teacher network. Similar to the Data2Vec framework, this teacher CNN is parameterized with an exponential moving average of the student CNN's weights. The distance between the embeddings output by the student network and the teacher network is then reduced via the Data2Vec loss. The composite loss function is as stated in the equation below, and the Data2Vec loss can be thought of as a regularizing loss representing the self-supervised component of the composite loss function. We conducted 3 experiments with different seeds to compare how our proposed BinImg2Vec framework fares against a model trained using just the softmax cross-entropy loss function. We found that over all 3 experiments, our proposed framework was able to consistently outperform the supervised-only training methodology by around 4% over a dataset containing 61 malware families. In addition, we noted the significant reduction in performance variation over the various runs. In particular, our proposed framework was able to reduce absolute performance variation by about 0.5%. To understand why this was so, we inspected the classification loss, or in other words, the softmax cross-entropy loss component, over the course of the entire training process. As can be seen from the graphs on the right, the classification loss of a model trained using the BinImg2Vec framework in blue is significantly more stable than one trained using just the softmax cross-entropy loss in red. What we can clearly see is that the additional Data2Vec loss is in fact helping to regularize the training process so that the model does not overfit to the current training sample. The eventual effect of this is the model's ability to better generalize to the test set and achieve a better performance despite having a higher steady-state training loss. The other effect is the reduced performance variation, since models trained by our framework tend to have a more stable loss curve on model convergence. Next, we try to dissect and understand the inner workings of the model. Recall that our model comprises a CNN, for which we intended to be a feature extractor, and a MLP, which we intended to be a feature analyzer and classifier. Here we study the output of the CNN, which is also known as the embedding layer, since it is supposed to embed information about its input. As the purpose of the CNN is to extract salient features for the MLP to analyze, the embeddings produced by the CNN should contain distinguishing features that can aid subsequent malware family classification. Let's see if it is actually doing what we expect it to do. As can be seen on the leftmost diagram, the embeddings produced by our proposed framework, even after projecting them into a 2-dimensional plane via the UMAP dimensionality reduction technique, are quite well clustered into the various malware families, differentiated by the color coding. This implies that the embeddings produced by the CNN are actually preserving features that facilitate subsequent downstream classification, and this is working as we desired it to be. On the other hand, the embeddings produced by a model trained end-to-end via just the supervised-only loss function results in embeddings that don't seem to be well differentiated in any way. Most of them are part of a big cluster, and this is an interesting finding, as it means that training the model in an end-to-end manner using just the supervised-only loss function results in non-interpretable embeddings. To understand why this is so, we turn to the Data2Vec loss curves that we logged throughout the entire training process for both our proposed BinImg2Vec framework and the supervised-only framework. Similar to earlier, the blue curve was the loss curve of our BinImg2Vec framework, while the red curve was that of the supervised-only loss function. Clearly, the red curve would be higher since the Data2Vec loss was not part of its loss function. However, what is interesting is that it is actually 2 orders of magnitude higher than the blue one. This clearly shows that it does not seem to be preserving the salient features of the input image. So, what this means is that our framework produces a CNN that actually preserves the features of the input. This is extremely useful, as we are now not only able to produce malware family classification probabilities as produced by the MLP, we are also able to produce meaningful embeddings produced by the CNN that preserves the features of the input. An example use case of these embeddings is the ability to verify the presence of new malware families. For example, we would expect the MLP's classification probabilities to be low for new malware families, and this can be further supported as we also expect the embeddings of the new malware family to not fall into any of the clusters shown here. To conclude, we have verified that the Data2Vec framework is also applicable to malware image binaries. We also showed how incorporating it with self-supervised learning can improve malware classification performances even in the cyber domain. Future work could extend this to even more malware families, or even malware functionality classification. Also, we noted that most malware types are now packed using a variety of packers. Future work could study the impact of different packers on the classification performance. Thank you.